The animal didn't cross the street because it was tired. One tiny word decides what that sentence means, it. You probably connected it to the animal without noticing. The animal can be tired. A street usually can't. But an AI model doesn't begin with that common sense answer written above the sentence. It has a row of token representations, and each one needs information from the others. The token it has to pull useful context from animal, cross, street, tired, and everything else around it. The mechanism that routes that information is attention. Here is the whole idea before we name the parts. Every token creates a question-like vector. It compares that vector with matching vectors from the other token positions. Those comparisons become weights. The weights control how much information flows back. Attention doesn't pick one magic word and copy it. It builds a mixture. The rest of this video will make that sentence precise, one visible operation at a time. In the previous episode, the word bank began from the same learned embedding in two sentences, a bank with money and a bank beside a river. Context pushed the two internal representations apart. Our pronoun has the same problem. Its starting vector says something about how this token is generally used. It does not yet contain the particular answer, animal, for this sentence. Put the sentence in one row. Each token already has a vector. Think of those vectors as compact states, not dictionary definitions. Now select it. If we simply average every token equally, tired matters no more than the. If we always copy the nearest token, street wins just because it happens to be close. Neither rule can adapt to what the sentence needs. Attention learns the routing rule instead. For one pass through one attention head, the model turns every token state into three new vectors. They are called a query, a key, and a value. Those names are useful as long as we don't take them too literally. Start with the query. The query belongs to the token whose representation we are updating. For it, imagine the query as a learned request for relevant context, not an English question, a vector. Every token position also produces a key. A key is the part used for matching. Animal, street, tired, and it all advertise different learned patterns through their keys. Then, each position produces a value. The value is the information that position can contribute if it receives weight. The key and value have separate jobs. The key helps decide how strong the connection should be. The value is what travels through that connection. A search engine analogy gets close. Your search is the query. The index entries act like keys. The retrieved content acts like values. But inside a transformer, all three are learned vectors, and the search happens for every token inside every layer. Watch the token animal. Its key may match what the query from it is looking for. Its value carries information derived from animal's current state. Street has its own key and value. Tired does too. Now the model needs a way to compare the query with all those keys. Place the query vector beside the key from animal. When two vectors point in compatible directions, their dot product is larger. When they are poorly aligned, the score is smaller. So the query from it is compared with the key at every allowed position. Our toy head produces one score for animal, one for didn't, one for cross, one for street, one for tired, and one for every other visible token. These are compatibility scores. They are not percentages yet. They can be positive, negative, or close together, and the numbers on screen are toy values chosen to expose the operation. A real model learns its own projections and scores. Suppose animal receives 3.2, tired receives 2.4, street receives 0.5, and the remaining positions receive lower scores. We can already see a preference, but the scale is awkward. A score of 3.2 doesn't mean 3.2 times as important. We still need a clean set of mixing weights. First, scaled dot product attention divides the scores by the square root of the key dimension. That scaling keeps dot products from growing too extreme as the vectors get wider, which helps the softmax step train more reliably. Then, the scores pass through softmax. Softmax turns the score row into non-negative weights that add up to 1. Our 4 visible weights might become 0.52 for animal, 0.31 for tired, 0.10 for street, and 0.07 spread across the rest. These are still toy numbers, but now they have a clear job. They control the mixture. Softmax does two things worth seeing. It preserves the ordering of the scores, and it makes the stronger matches compete for a fixed total of 1. It does not certify truth. A large attention weight is not the model saying, "I am 52% sure this is the correct explanation." It only tells us how strongly this attention operation will mix one value into this output. Now the flashlight metaphor can go away. Nothing in the model is literally shining a beam. We have a query, keys, learned compatibility scores, and normalized weights. Only one step remains. The values have to move. Take the value vector from animal and multiply it by 0.52. Take the value from tired and multiply it by 0.31. Scale the other values by their smaller weights. Then add the scaled values together. That weighted sum is the attention output for the query from it in this head. This is the distinction that makes query, key, and value click. The model does not average the keys into the answer. Keys determine the routes. Values carry the information, and it doesn't have to select a single winner. The new representation can receive strong information from animal, supporting information from tired, and weaker information from the rest of the sentence. That is useful because meaning is rarely one clean arrow. The token tired helps establish the kind of relationship in the sentence. The token animal supplies the likely referent. Other positions can contribute syntax, boundaries, or context that our simple picture leaves dim. After the weighted values merge, the representation associated with it has changed. Later components and later layers can keep transforming it. Attention is the information exchange, not the entire transformer block. So far, we have followed one query. The real operation is larger. Move back from it and restore the full sentence. Animal creates a query too. So does cross. So does street. Every position can compare its query with the keys from the positions it is allowed to see, then build its own weighted combination of values. Stack all the query vectors into a matrix called Q. Stack the keys into K. Stack the values into V. When Q meets the transpose of K, every query is compared with every key. The result is a square grid of scores. One row belongs to it. Another belongs to animal. Another belongs to street. Scale the grid, apply softmax across each row, and the grid becomes an attention matrix. Bright cells carry more weight. Dark cells carry less. Multiply that matrix by V, and every row receives its own weighted value mixture. The grid can look like a map of which tokens influence which outputs in this one operation. It is useful evidence. It is not a full transcript of the model's reasoning. Researchers have shown that attention weights do not always track other measures of feature importance, and very different attention patterns can sometimes produce similar predictions. A heat map is a window into the routing, not a complete explanation of the whole network. Now, the compact formula has nothing left to hide. Attention of Q, K, and V equals softmax of Q times K transpose, divided by the square root of the key dimension, all multiplied by V. Q times K transpose creates the comparison scores. Dividing by the square root keeps their scale under control. Softmax turns every score row into mixing weights. Multiplying by V forms the weighted combinations. The equation looks dense because it compresses the entire animation into one line. It is not a different idea. Return to the opening sentence. The query from it compares with the keys. Animal and tired receive strong toy weights. Their values contribute strongly to the new representation. Street contributes less. The output now carries the context that helps later layers treat it as connected to the animal. That answers the episode's question. Every token decides what matters through learned vector comparisons, normalized into weights, followed by a weighted mixture of information. But one routing pattern is not enough for all the relationships inside language. A useful connection for pronouns may not be the useful connection for word order, quotation boundaries, nearby grammar, or a subject many tokens away. Transformers solve that by running several attention operations in parallel with different learned projections. Those are attention heads, and they are the next piece of the machine.